Good afternoon. Thank you all for being here today. I'm Eric Davidson, President of the American Geophysical Union. I'm very pleased to introduce our agency lecture for the fall meeting of 2018. When asked what science means to him, our speaker simply said, the name bestowed on our largest rover on Mars, Curiosity. Although I imagine if you were to ask him today, he would probably also say curiosity and insight. Dr. Jim Reilly is the director of the United States Geological Survey, where he leads more than 8,600 employees, including scientists conducting research in every state as part of the nation's largest water, earth, and biological science and civilian mapping agency. While USGS scientists do indeed conduct curiosity-driven research that provides insights into how the Earth system works, their science also has very real applications, practical applications. The USGS collects, monitors, and analyzes data about resource conditions, and by providing reliable scientific information, USGS helps minimize the loss of life and property from natural disasters, manages water, biological, energy, and mineral resources, and enhances and protects our quality of life. Prior to joining USGS, Dr. Reilly served as a subject matter expert on space operations and as a technical advisor supporting National Security Space Institute of the U.S. Air Force. As an astronaut at NASA, he had a distinguished 13-year career that included 3 spaceflight missions and 5 spacewalks, totaling more than 856 hours in space. Before his service with NASA, Dr. Reilly served as chief geologist at Enserch Exploration, Incorporated, working on projects around the world, including Antarctica and the continental slope of the Gulf of Mexico. It is my honor to introduce to you today Dr. Jim Reilly. Please join me in welcoming him to the stage.
Thanks very much. All right, good afternoon. So first thing, as the head of the USGS, I know we have a few people here, so I'm going to ask, who are my USGS people here? Where are you guys? Outstanding. I am the director of the USGS, and I say that because I was down at the information desk about an hour and a half ago, and standing there waiting for somebody to tell me where I was supposed to be because I don't know where I was supposed to go, and a USGS employee walks up and goes, "Hey, do you know where I can buy a cup of coffee?" Yeah, right over there. I'm somewhat kidding on that, but one of the great things is I've been here 7 months as of yesterday, and so it seems like 7 years already. What I'm going to talk a little bit about today, and I apologize right up front, I can't stand still or sit still, so I'm going to be wandering around the stage a little bit, so I apologize to the guy with the video having to track me, and hopefully you won't find it too distracting, but I'm going to talk a little bit about the USGS and where we are and where we're going. And the bottom line when we get into this, USGS is all about the science, and that's my role in it. In fact, if somebody had asked me just 5 years ago, do you think you'd ever be the director of the USGS, I would have laughed first and said, not a chance. In fact, when I got the phone call to come interview, I hadn't put my name in for the job. It was apparently somebody else had seen some benefit of my experience so that I could become the director of the USGS. And of course, now I'm here, and 7 months in, it's been a great run so far. Had a blast. Every day I learned something new. In fact, I'll talk a little bit about a few of those things today as we walk through it. But I wanted to talk a little bit about where we are with the USGS and where we're going. And so people ask, what's your vision? So we're going to talk a little bit about that, but it's not my vision. It's really the vision for the USGS. So as we're stepping into it, the world, as you know, and AGU is certainly in the middle of it here with the conference, it's changing. Science is moving very quickly. And so we're, of course, having to respond to that as well. We're facing new challenges in pretty much every discipline that we have. In fact, we're even blurring the disciplines a lot. In fact, in our mission areas, we no longer have a geology or a geophysics or a geochemistry or an ecosystems really sole stovepipe. They're actually now relational. So when we look at the geology piece, for example, we now have energy and minerals. And so when we have ecosystems, it's still ecosystems, but it covers the spectrum of ecosystems, everything from environmental health to pollution to climate change. All of the things that we have within that realm are now within these mission areas. And so we have currently 7, and we're making 5 just to simplify our budgeting process, which is, if you've ever done any of that in the government, which I had never really done before, it's a really arcane process in terms of how things operate in the budget process. So I'm learning all of that piece, but the things that I want to talk about are really sort of bigger things in terms of larger initiatives on where we are with the USGS. And that's what we're going to talk about here as we walk through it. So I wanted to talk very briefly about who the heck am I, right? So as Eric mentioned, I was fortunate to fly 3 missions into space as an astronaut, which is what I always wanted to be when I was growing up, and I was lucky enough to get there at the ripe age of 40. But by that time, I'd already had 17 years in the oil industry, and as part of that, I spent about 22 days underwater looking at chemosynthetic organisms, which are about the equivalent to finding something alive on Mars in terms of its relationship, the life's relationship to what we're used to, and that's the photosynthetic systems that we all operate within. And then on the upper right, you see a picture of me in Antarctica back in 1977, 1978, and I was taking some samples of the granitic intrusives and looking at the geochemistry and the stable isotope geochronology on those systems, and established the relationship in Marie Birdland that extends all the way up through the western margins of South America into North America, all the way up into the Aleutians in terms of the geochemical relationships and the leading edge back in the Cretaceous. And that was a blast. I had a great time. 4 months out in the field, and that was not what I was intending to be. At that time that picture was taken, I was just getting a master's, and I was going to come back and become an airline pilot. But that became my career, as becoming a geologist. And it was that point right there, pretty close to it, where I pretty much had made that decision that, hey, this geology stuff is a lot of fun. I was doing it because I liked it, and I was doing well in it, and then all of a sudden I'm getting job offers. So that led to becoming selected as an astronaut in 1995, flying 3 missions, 1 to the Russian space station, 2 to the International Space Station. People asked, what was the best thing about flying in space? And that was actually an interesting question to have to answer because there's so much to it. But I realized that there were 2 things about it. One is the most important thing about flying in space is changing your perspective. And that's probably served me better than anything else I did while I was at NASA, and I did a lot, and they taught me a lot. The second was the most important thing that you realize when you're at NASA are the people that you work with, the people that you fly with. I sort of knew that, but it really becomes obvious when you're strapping yourself to 3.5 million pounds of high explosive with 5 of your closest friends, and you have to make that decision that, hey, we're going to light this thing and go to space in 8.5 minutes from here to 17,500 miles an hour. That does sort of focus your attention a little bit on what's important about that point. And then now I'm the 17th director of the USGS. And so that's sort of neat because I was number 372 into space in terms of the total population. I thought that was pretty impressive until that happened. And then I became number 17 as the USGS director. Following number 2, who everybody knows, John Wesley Powell, and so he's sort of my mentor, if you will, in history and tracking that. Now, where this picture was taken, you'll notice Secretary Zinke there on the right. We were there at the Kilauea eruption site just after the thing finally quieted down, and the guy in the middle is one of our scientists that is using a UAV, or a drone, if you will. And for the first time out there, we were using this technology, which isn't anything new. But we were using it to do the collection of information and data on the gases and the lavas associated with that eruption and tracking where the eruption site was moving to and where the lavas were flowing to, and providing that as hazards information in the immediate sense to the local and state officials. But then the second piece was acquiring the data that now allows us to get a better understanding of what's actually happening in the magma chamber within the Kilauea eruption site. And with that, we're taking these collections now with the drones, which does two things. One, it gives us very rapid collection. So we got something like 2 terabytes of data in 1,200 sorties on these drones. Second is it took our people out of the hazard zone. And so nobody's in that cloud anymore collecting gases. We're now sending what are essentially expendable drones, so that even with all the equipment that we had hanging on them, it was a grand total of something like $25,000. So the fact that, they come back, we have to take them apart and put them back together again, that's a heck of a lot cheaper to just send one of those things in there than it would be to send one of our human observers in there, even though that's what geologists want to do, right? And they were actually disappointed. We had to go out there and say, no, you can't put your boots on and you can't go into the cloud and you can't sample the lava anymore because we're going to do that this way. They were all disappointed, as I would be, right? But it takes them out of there and we're able to get it a lot faster. So that's one of the things. I'm going to come back to that theme here in a minute, and that's the change in perspective. How do we get this information faster? What do we do with it? That answers some of the questions that we have to supply. So when I first walked in, I was like, what is the USGS, right? I had a pretty good idea, having worked with them on a number of projects in the past, but I had to step back and say, what's the mission statement? So as a systems engineer, which is what I was doing with the Air Force and with the Navy, you first start out with your mission statement, then look at goals and objectives, and that becomes all the things that you do, and all those things become requirements. And that's where we are most of the time in an operational sense. We're in requirements pretty much day to day. But I had to go back and say, what do we do? And it actually comes out very well in the Organic Act of 1879, which formed the USGS, and that is classification of all of our public lands and examination of the geological structure, mineral resource, and products of the natural domain. And if you think about that, almost everything fits in that statement right there. Almost every product that we are associated with, no matter what it is, fits that mission statement. So it's still the same as it was then. Now our bigger mission, though, is taking all these things and now applying it, and applying that science and becoming the science advisors, in our case, to the U.S. government. And so my job is literally to act as a science advisor to the Secretary of the Interior, who acts as the advisor to the President on the interior matters. And so that's our basic job. But more critically for us as the USGS, I'm just there as the director. Our job is to describe and understand the Earth. Makes sense? Minimize loss of life and property from natural disasters. That's a big part of what we do today, and we're going to talk a little bit more about that. Manage water, biological energy, and mineral resources. Those are all the natural domain for our country. This is what we do. We find out what have we got, how do you apply it, give that information to the government, but also to the private sector and other users, right? So it goes across. Our customers are literally, I could probably say, even our USGS fellow employees in here, everyone in this room is our customer in one form or another. So you're our customers. So we provide this information to you. And last is enhance and protect our quality of life. And that's a pretty broad spectrum right there. When you look at that one as being as an objective, that pretty much covers everything in the natural realm. Now I did a little crosswalk between USGS and AGU, and we won't walk through all of that, but you can get an idea pretty fast that pretty much what we do in the USGS is pretty much what AGU does, but in a separate NGO sort of level effort. And so there's a lot of this stuff that we combine, which is why there are so many hands that came up from the USGS when I asked who's here. Because this is one of our primary places where we take all the information that our scientists are working on, and this is where they bring it to put it in the public realm. Nothing happens until you put it out there. And so that's what our focus is with AGU. The AGU is our place where we put this information out. And so you'll notice things like advance the understanding of the geosciences, advanced geoscience discoveries, all those things, get that information, put it out to the public realm so people can use it. That's why we're here. And so bottom line, we really have the same customer overall, and that's our country. And that extends even past the national boundaries when you start thinking about our international relationships as well. And you could even say we have the same customer, and that is, when you get to the bottom line, the planet. And so there you have that in terms of our big picture. USGS budget, I'm not going to spend a lot of time on this because it'll bore you to tears, but this is where I live most of the time, trying to figure out how to make all this stuff work. And so you'll see on the right side we have our mission areas, and those are our strategic concentrations of what we're doing. Notice ecosystems, land resources, energy and mineral resources, environmental health, natural hazards, water resources, core science systems. Core science systems is basically the mapping, the land mapping initiative, the Landsat systems, all those things that basically form a foundation. And we're going to come back to that in a little bit, because that foundation now allows you to hang pretty much everything else against it. Science support, which is more or less our administrative function, but we record that separately. And then at the bottom is facilities, and that's actually one of our biggest challenges, and that's one of the focus areas as the director I'm looking at right now, is trying to get good, 100% functional and livable facilities for all of our folks. And we have some challenges there, because a lot of facilities have been around for a long time, haven't really been updated, and so we're trying to fix that. But to fix that, it costs a lot of money, so you'll see that reported out. Now we notice that there's actually two parts to the program. This is enacted. This is in the federal government's budget. This is what we get as allocated or appropriated money. And so it's about 1.1 billion-ish, right? And then we have another piece, and that's our reimbursable. That actually comes from our customers and our collaborators. And notice that it's scattered all over the place, but the biggest one you see there, the blue, that's water. Water, of course, is the critical resource, no matter what you want to look at. And that's a component that is one that we are working very hard and have the largest amount of people and the largest effort going into characterizing what's our water resources. And as you know, I'm a Western boy. I was born in Idaho, lived in Oregon, Washington, California, spent most of my time in Texas. My last place I was living was in Colorado. Every single one of those, in one place or another in the state, has a big challenge in front of it in terms of water. So I get that piece, right? Here in Virginia, if you're from Virginia, especially this year, not so much, right? We've had a lot of water here, so it doesn't seem like it's much of a problem. But out west, it's huge. And in fact, if you're from that region or you work in water, you know what some of the challenges are out there. In fact, the Colorado River Compact right now might trigger this year, and when that happens, and all of a sudden one state has to give up water to another because this agreement that was signed, what do you think is going to happen next? Right? There's going to be a huge amount of fussing going on about who owns what water and who's got the rights to it and all of that stuff. The lawyers will get involved, and then the government will get involved. So we've got to figure out how this resource operates. And so that's both surface and subsurface, as well as all the atmospheric components. And so we work a lot on that. And that's where you see a lot of reimbursable. It comes from the states and from other organizations that are looking for, including the Corps of Engineers, looking for information on where is the water, where is it today, where is it going, where are the resources, and how much can we use, and what's it going to look like over time, which then gets into the ecosystems piece. And so we have all of that out there. So we really are about a $1.6 billion agency with our 8,000 or so people. And so that's what we operate with. That's the boring part. Let's talk about some stuff that's a little bit more fun. And so I got asked this question before I went and did the GSA talk, and they said, what are your big missions that you want to accomplish? What are your themes? Well, I had to think about that, because at that time I'd been on the job for just a couple of months. But basically what I was able to do is boil this down to, from our mission areas, what are the 4 big areas that we're focused on right now? And as you'll notice, right up at the very top is big data. Well, what the heck does big data mean? Right? That's sort of a buzzword, and it can mean a lot of things depending on who you are. For us, of course, big data is literally that. We have huge data sets. Just the water alone is a huge data set. What we're doing with the 3D elevation program in terms of the LiDAR acquisition at 1 to 12,000 or 1 to 25,000 scale, coming down from 1 to 100,000, it is not only a big data set in its own right, just in the number of data points that are there every couple of centimeters, but what that also means to us is an ability to characterize that water environment where we can see roughly 10 times as many stream reaches as we can at the existing scales that we operate at with our existing data set. So in the course of doing the math on that, we have roughly 18,000 stream gauges out across the countryside. So if you get a 10 times increase or a 10-fold increase in what you can see, because you now have the resolution in the LiDAR data set, you now have to get 180,000 stream gauges to get the same density and quality of information. Well, that's a big challenge. Right? Now, trust me, we do not have the money at the USGS to be able to get another 170,000-ish or so stream gauges to be able to accomplish that. So we're going to have to figure out how to do something differently. That's where we get into the big data. How do you characterize this by using the data sets that you have available to you and then get that information out? Another piece of it is we're going to take that 1 to 24,000 scale data set and we're going to go to 1 to 5,000. So once we finish the 1 to 24,000, which is at about 47% complete according to the folks doing the work, Kevin Gallagher, who's our missionary lead for that program, tells me we're about 47% in acquisition in the lower 48. In Alaska, we're at about 97%, so we're actually a little bit farther ahead up there. But that capability is now going to allow us to do a national water model with NOAA. Right? So now we can literally, what we hope to get to, and this is a conversation Tim Gallaudet and I had the other day, what we hope to get to is you and I can click on any stream anywhere and figure out what's going on in that stream reach or within that watershed today. And so you can get almost real-time information. But to be able to do that, you have to have, one, a big data set, but even more critically, you have to be able to interrogate that data set and get that information back. That's a big data piece, but it's all about what can you do with it. And this is where some of my background with the military comes in handy, because the NRO does a lot of work for the intelligence community side of things in characterizing the battle space for the military. And so what are they trying to do? They have huge data sets to characterize what the other guys are doing. And they use this Internet of Things, which is a set of relationships, is where a lot of people are at right now. The NRO is actually looking to go to the Internet of Action. And so what they want to do is take all that information, shove it into the cloud, turn it around, have an artificial intelligence or machine language capability on the front end that processes that information, so that if you do a query for a piece of information, let's say on a stream reach in Colorado, for example, the first thing you see isn't just a bunch of data. The first thing you see is the information that says this is what's going on exactly in this place at this time. So you have something that you can do something with right away. That's the Internet of Action. And that's a big data piece, and that's across everything we're doing. So when you think of water, water pretty much covers the entire spectrum of how we operate on the planet, particularly when we get into ecosystems, which you notice is down there on the bottom. And I use the water there specifically because a lot of what the ecosystem managers have to face, particularly at state and local levels, is the quantity of water that's available and managing that resource. And there's always tension between using the water and leaving it in place. And that's part of our job, is to help them realize how well to do that, what has to happen, what resource have you got. Critical minerals, and really it's not just critical minerals, it's all minerals. And basically anything we use that comes out of the earth, which is a lot, as you know, those minerals are things that the USGS is charged with understanding and being able to provide that information. But the Secretary recognized as we walked into this 21st century that we have a very distinct dependency on a small group of minerals and elements, and there's about 35 of them, that if we don't have them, all that electronic stuff that you and I like to have, we don't have it. Right? And some of those things we don't have, or at least we're not producing. So that's part of that list. So understanding where these resources are, how much we've got, what would it take to get it out, what are the impacts to getting it out, all the things that you have to address as part of the public realm. That's what we do as far as the minerals and the minerals extraction. But first we start with the resource. Where is it? And with that, there's a lot of effort that goes on with our states. And so when we talk about collaborators, and you saw that money that we got from reimbursables, that's a lot of where kind of information comes, or where that money comes from, because we're charged with providing that information. Again, we're the big science advisor. Hazards, right? Hazards are things we're trying to characterize all over the place, right? So we just recently had an earthquake up in Alaska that was sort of an eye-opener in terms of the size and impact of it. But just before that, about a week before that earthquake occurred, we actually had inauguration of something called Shake Alert in California, which is a test of an early warning system for earthquakes to try to minimize damage to the populace. And so this follows on to some systems that the Japanese have been using in their country for a while, and also Mexico City has been using it for a while as well. And what it does is it just measures the differences in the arrival times between P and S waves. And by measuring that difference in the arrival, you can characterize it, give the local communities in the states some early warning that says you might have 20 seconds or 120 seconds. isn't much for you and I, but it does mean a lot to SCADA systems, for example. So if you have the indications that you're going to have significant damage in an earthquake with an S-wave arrival, you can start shutting off the gas supplies within the system so you don't end up with those big fires that everybody remembers from the Loma Prieta quake in California in 1984. The gas was still on and the houses burnt, and they had significant fires in response to that. Now we can give you a little more information. So we're going to continue working on that. In fact, in January 3rd, Mayor Garcetti and I are going to be giving a little press conference there in LA to talk about that. And then we want to expand that and take it further. Volcano early warning, the same thing. It's along the same lines, right? How much warning can we give you, particularly in the Northwest and Alaska, of a significant eruption? And that's not only for the local area, but also for aviation. So one of the things that you remember from the Iceland volcano is that it threw ash into the stratosphere. We basically grounded air travel between the US and Europe for several days, if not weeks. And so those are impacts that we need to be able to characterize. And so those are some of the hazards. Other hazards are landslides, soil movement, soil liquefaction. Hazards also include everything from pollution trains to water quality. It covers pretty much the entire spectrum of things that you might expect that we would consider to be hazards. And our job is to try to characterize those hazards as best we can, try to get in front of them so we can give you some warnings and get out with those. And with the ecosystems, I talked a little bit about that, and we're going to talk a little bit more about that here in a minute, because it's all about what are things doing right now, what are the things that changes within them. Big question is, how well do we understand them? And we understand some aspects of it quite well, other aspects not so well. And I'm going to give you a case that will illustrate that here in just a minute. So on the big data, 3D elevation program, we've talked a little bit about that. Hydrologic mapping. So we have both surface and subsurface waters. Surface waters, the stream reaches, 10 times more. In the 1 to 24,000, we go to 1 to 5,000. We got another 10-fold increase in what we can see. When we do that, well, we've gone from 18,000 to 180,000 to 1.8 million stream gauges to get the same data density. Obviously, we've got to do something different there. Now, that's the surface water. We also have the subsurface water, which in many places is the more critical aspect. Where I grew up in Texas, we had both surface water, which was the drinking water, the water that was used within the public supply systems, because the subsurface water become unreliable. You get out west in Texas, there's a lot of agriculture out there which is totally dependent on the subsurface water. Understanding what that resource is a challenge that's been there since the 30s, and we're still working on that. But even more critically, what's the linkage in this water model that goes from the surface to the subsurface? And so there's a huge amount of work that's being done right there. Again, lots of data, and we're going to have to figure out new ways of taking that information, putting it into the cloud, and be able to turn that around and give you that Internet of Action in water right away. Mineral mapping, that's all about how well can we resolve information. So when we get to these critical minerals, which we'll talk about in a minute, a lot of times the outcrops where these particular ores or the minerals are present aren't very large. And so the current way we look at Landsat, and Landsat 9 is going to launch still on schedule for December of 2020, what's Landsat 10 going to look like? Well, by looking at the minerals these days, we're now changing our perspective on that, and I'll touch on that here in a minute. So what are the critical minerals? Right? We've talked about that a couple of times, and what makes them critical? Well, there's the list. I won't bore you with the details, but really all you need to look at there is in the colors. If it's yellow and orange, that we probably don't recover them here in the United States. So we're dependent on foreign sources for most of those critical minerals. Now, what do we use them for? Well, because I work for one of these guys, a Navy SEAL, pretty much everything they use to give them an advantage on how they sense the world around them, and the key thing is sense the world around them, is dependent on those minerals or elements. And for us, you and I, it's that thing right there. None of this would be available if we didn't have access to those minerals and elements. particularly the ones in yellow. So the big question is, where is it? How much have we got? Can we get it out? Can we get it out effectively? Can we get it out safely? And safely, of course, covers everything from human safety to ecosystem safety, all those things that we're charged with managing. And so we have to look at each of those. And we have a big project underway right now in concert with all the states. And what we're finding is, as I mentioned, a lot of the outcrops of where these minerals might be aren't very large. In fact, many of them are not even the size of one of the segments of chairs in the room here. So we have to change our perspective on how we image for this, which means, what are we going to do with Landsat 10? What kind of spatial resolution do we need? What kind of spectral resolution? Temporal, not so much, but certainly spectral and spatial is critical. So we're changing the way we look at Landsat 10 as an architecture. In fact, it's probably not going to look anything like Landsat 9. It's probably going to be a disaggregated architecture. In other words, it's not going to be one single satellite. It's very likely to be a system of systems. In other words, we're going to have a piece. There's going to be the private sector that's going to have their piece, because commercial space is becoming very much a game changer and a player. And so now we need to figure out, what do we have to have, and how do we shape it so that we can get that information so that you and I can still have the next generation of iPhones without having to worry about maybe an unstable regime or an unsavory regime or somebody who's not necessarily your friend controlling the minerals that are critical for that capability. Natural hazards, it covers everything you see there. Hurricane Florence, what do we do about that? NOAA tracks these things. We actually look at the coastal change and the impacts that happen after, during, and after. In fact, if you've probably seen, as we were getting ready for Florence, Michael, and other storms, we have a USGS team, sort of a flyaway team, that goes out in advance of the storm and puts the flood monitors and the stream gauge, portable stream gauges out, so we can characterize what's actually happening. We can tie that now to the NOAA data, which tells rainfall rates and location. We can look at what's happening in Houston, for example, when the water's backed up through Brays Bayou into downtown. How much is there? Where did it come from? Where did it go? How long did it take to leave? And then also, in addition to that, we do the sampling, so we can tell you what's in it, which sometimes can be quite surprising. So all of that, of course, helps us characterize the level of threat. And so now we can give you a better idea of, what do you have to worry about? That's the bottom line. Ecosystems, how well do we understand that place? Reasonably well, you might say. I'll argue that we don't understand it well enough, and that we have a lot of work to do to understand all the interrelationships. You know, if you think of just the chemistry of the ecosystem that we operate within, it's incredibly complex. And right now we're trying to characterize the ecosystems and specifically look at it in terms of, how is it responding to climate change? That's an important question. What's happening? Well, for us, we have to look at it and then try to figure out, okay, so this is what we think the trajectory is likely to be, get a better understanding of the variables. And then the latest AR5, if I remember correctly, there's roughly 1,000 variables in all the different components that are used to give us the models that now tell us what we think is possibly going to happen. How well do we understand? Is 1,000 variables enough? Probably not. There's a lot of things that when we talk to the modelers, and I spent actually 3 days with the folks at NCAR right after I went to work 7 months ago, because I'm not a climate scientist, and I wanted to know, what is it that I need to be thinking about and worried about? And we spent 3 days walking through it, and we have a lot of things that we still don't know, but we will, right? And that's the critical component. And so we're constantly measuring them, looking at how do they operate, what's critical for a healthy ecosystem, and of course that ecosystem can everything be from deserts to swamps to the oceans to the coastal. It's everything. How well does it operate? And what do we need to worry about? What are the critical drivers? Some of them we know, some of them we don't know. We have to figure out the ones we don't know, apply them, and get a much better answer for what we're trying to do. And this is the challenge, right? So when I first looked at this chart, which is the AR5 spaghetti chart that you guys I'm sure are familiar with, which trajectory do you follow? Well, there's lots of philosophy on which one you could follow. Now, the reality is, just from a statistical standpoint, it's probably neither end member, so somewhere in the middle is where you're going to be. But if you wanted to go out to 2100, that's still a really broad range. And we have to be able to say, with at least some certainty, that we're going to be within this envelope that you can plan with. And so it became a difficult challenge for us. And so we were looking at it. You can do one of two things. You can reject it completely, or you can say, well, just to err on the side of caution, we're going to take the worst on worst case, irregardless of whatever those probabilities might be. We don't have that luxury. We have to be able to provide something a little bit more deterministic from the standpoint of what we see in what we think might be the changes, and continue to work on getting there. So we're involved with the U.S. Global Climate Change Research Program, and we're part of that with the NCA4. Now, there's been a lot of challenges with NCA4, and we'll probably address that in the questions later. But more critically, when we get to ecosystems, what are the things that we have to look for that are the critical factors, and what's going to happen over the next 20, 30, 40 years? How far out can we push that and still stay within a statistically relevant trajectory? And so what we've done is we've worked with the folks there at NCAR and looked at that and said, well, we can get out there, as you see, it stays pretty tight out to about between 2040 and 2050, and then the variables take off, right? So which one do you want to follow? Well, let's just avoid the end member. Let's go out to 2050 and say that's where we're going to start, and we're going to say this is where the trajectory is going to go. And then in 5 years, let's take another look at it and look out 10 years. Another 5 years, 10 years, and look back at the same time, so that make sure that we're on the right trajectory, so that what we have is essentially a more pragmatic way of looking at some of the characteristics, and help us at that time as well, as we get more and more of these variables identified within the ecosystems. We now have a much better assessment of what's really happening. Now, here's the challenge I want to pose to you. Right? So if you want to go to Mars, let me ask a question this way. I was going to ask how many have seen. How many have not seen the movie The Martian? I don't see anybody's hand going up, right? Well, there's 3, 4. You guys all need to get a life. Go out and see a movie, right? It's actually a pretty good movie from the standpoint, but it does one thing. It uses physical-chemical processes to do the environmental support for the crew. Now, the problem here is, and this is one that I posed to my systems engineering students at Stevens when I was doing some adjunct work there. I said, come up with what it would take to do what they did in The Martian for a crew of 5 for a 540-day mission, which is what the round-trip mission would be to Mars. The answer is about 18 Saturn V's worth of stuff has to go to orbit, assemble it together in a spacecraft, send it to Mars. That's one mission. You think we would find the money to do that? They couldn't do that. They could take all of NASA's money, all of the USGS money, plus several other agencies within the Department of Interior. They couldn't touch the Department of Defense, but if they take all that money, you still can't get there, right? Because we never built 18 Saturn V's. For the entire moon program, the Apollo program, we built 15. And so now you're building more spacecraft or launch vehicles than we've ever built to get this stuff just to space to get one mission, right? So that's not going to work. So how do you do that? Well, we're going to have to figure out how to build a small Earth, stick it inside that spacecraft, get it running, and then launch it to Mars, because now you're going to recycle everything. In fact, if you look at what you have to do, you're going to be recycling about somewhere between 95 and 99% of everything. To put that in perspective, each and every one of us today, from the time you got up to right now, each and every one of us individually has thrown away or used and discarded more than an entire crew could discard for a 540-day mission. That is an interesting challenge, right? So when you get to it, we really don't understand the ecosystems well enough. So do we need to? Absolutely. Do we need to continue working on it? Absolutely. Because anything we do in this particular case, and this is just an example, of course, that information now comes back, and we can use that to help us operate better here on the planet. The more efficient we are, the better off we are, the more resilient and the more regenerable our systems are. But a lot of things about Mars are interesting. InSight is there on the surface. One of the coolest things about what we got out of Curiosity, in my opinion, is the fact that they see methane on Mars, and it's seasonally variable. So in the summertime, as things warm up, you see an increase in methane in the atmosphere. What's the source of that methane? That's an interesting challenge, right? It could very well be a very simple form of life. In fact, one of the things I love about the concept of going to Mars with a human crew is you might be the first person to see ET. Now, it'd probably be through a microscope, but you will have potentially that opportunity to see it because it has all the right requirements. It has water, If there's methane available, which we're obviously seeing it, but you don't even have to have that because there's chemicals on the surface and in the near surface that we know will work in chemosynthetic organisms here, well, now you have all the things you need. So could we do it? Absolutely. But we're going to have to think differently. Getting back to what's the most important thing I got out of being a spaceman? Thinking differently, just changing perspective. So sometimes just stepping back is definitely worth doing. So the other thing, and that's a big item for me, is again why I asked people to raise their hand from the USGS. We got a lot of great people. In fact, that's one of the best things about my job is all the people that I get a chance to work with. In fact, that's what I tell people about what do you miss about being at NASA. I don't miss the meetings, right? And I won't miss the meetings when I leave the USGS, but I will miss the people because we got really, really good people. In fact, I didn't bring it out here, and I was intending to, and I just forgot to, is that on my desk day before yesterday was a stack of 40-year and 50-year certificates. And these were individual pieces of paper. They're that thick for the next 18 months. That's how many people, though, we've had that have been there 40 and 50 years. That's a good news, bad news story, right? So good news is people love their jobs. They come to work, and they are still there. Bad news is they're still there. No, I'm kidding, right? But the bad news part is because they're there, one of the problems we have is we have a very shifted demographic. We have a very mature workforce and not a very young workforce, and so we're looking to change that. So we're looking for ways to bring the young workforce in, and good news is we're doing it. We're still getting the young people come in. USGS is a destination for a lot of people, and it's great. It's like NASA, right? You grow up and that's where you want to go. And when you get there, a lot of people stay there their entire careers. Now, the one bad news part of that is that if you stay there your entire career and don't move around, then you end up with a culture that's very unimodal. In other words, you don't really have that change of perspective. So one of the things we're going to do too is we're going to look at mid-career executives and scientists, and we're going to look at doing swaps. In fact, Tim Gallaudet and I have talked about that in terms of NOAA folks coming our way and USGS folks going their way, and then swapping them back. And now we've got this cross-pollination and ties our organizations together. And we're going to do that inside the Department of Interior as well. And so that now gets a much more rounded workforce. You're welcome to stay 40, 50 years, but one of the things that we want you to do is you're not going to be the mentor for the mentees, those new guys coming in. One of the things we really do well is one that I really like, and this is one of the few places I've ever seen it, is that we have what's called the Emeritus Program. And so we have scientists that retire, and they are now working still with USGS, even in retirement. And so we don't pay them, but we give them their lab space, office space. They give them a little bit of money. I'm looking to try to get them some money so they can come to conferences like this and bring their mentees and transfer that knowledge that goes from them to the young folks. So our workforce development is critical. And that covers all the spectrum. So that's not only just getting the young people in and replacing us old folks, but it's also a diversity of our workforce, right? And good news is USGS actually has a relatively diverse workforce, but we could always be better, and we're focusing on that as well. So that's one of our big challenges. But when you look at it, in 1963, it's all a bunch of guys there in Flagstaff. But in 1987, there's a lot of women, and then when you get to our workforce later, there's a little bit of everybody there, right? So, but there could always be more, and we're going to be focusing on that. And then I love this picture because you probably saw this one, and this is people coming out to take a look. This is a combination of both hazards, the Earth science system, core science systems mapping, as well as the geochemistry piece. So it sort of wraps up a bunch of stuff, but this picture actually came out and went viral. And if you'll remember, there was actually a cautionary statement that came out from the USGS that said, this is probably not a good place to roast marshmallows, and that's probably true. It probably wouldn't taste so good anyway. But people were vastly interested in what's going on here. That's one real advantage we have at the USGS, in that people naturally gravitate to what we do, right? The fact that there's a volcano out there, USGS is on the back of our jackets or jumpsuits, whatever people are wearing when they're out there, that's a great advertisement for what we do, because we work, as we mentioned at the very beginning, we work for the people of the nation. So we work for all of you. When I say you're our customers, you are certainly our customers, everyone out there. And we spend a lot of time working on all of this so that we can characterize this, better understand it, so that we hopefully get better warning, better information on what's going to happen, because we always get surprised, and even in Kilauea, we got surprised on where the flows were going. They actually took a path we didn't anticipate immediately. So getting that information, then looping it back in, now becomes a base of information we now put out there. And so why do we do it? This is the one that I love the best, T.S. Eliot, and I've been using this one for decades actually. And then he said, we should never cease our exploring, because at the end of our exploration, we're going to see the place where we started and see it differently and see it all again for the first time. It's all about changing our perspective. As I mentioned, I never saw this. This picture was actually taken by Jack Schmitt from Apollo 17. We were a lot closer to the Earth than that, but the perspective is the same. All those things that you and I see as differences here on the ground disappear in space. You just don't see them. There are no borders between nations in space. You don't see some of the differences that you might see politically in space, obviously. So it's really all about the planet, and that's what we do at the USGS. It's science for the planet. That's what we do. So with that, I want to thank you very much for the opportunity to come see you. I understand we have an opportunity to have a little discussion and have a Q&A session here, so I'm looking forward to that. Again, look forward to hearing from you. If you have any questions, comments, USGS, I'm actually easy to get a hold of. It's jfreilly@usgs.gov. Right? Feel free to send a note. If I can't get back to you, trust me, it's because I get about 1,000 emails a day. And I will guarantee I'll have read it, and if it's a comment that's something that needs a remark that comes back, you might hear back from me or you might hear back from somebody in our organization. But we really appreciate the opportunity to come speak to you today, especially given the tight connections that we have with the American Geophysical Union for years and decades, and we'll keep that going for years and decades in the future. Thank you very much for the opportunity today. Thanks, sir.
Well, thank you, Dr. Reilly.
Sure.
It was really informative. And I want to, so I had asked members to submit some questions to me, so I have a variety of them that I know that our members are interested in. But I want to touch on one of the things that you brought up about improving our ability to predict natural hazards. You were talking about making improvement, how important it is just a few seconds for earthquakes. And then you mentioned working with NOAA with floods. You know, we already are pretty good at predicting, and as you said, with the things that working with NOAA and improving rainfall and also USGS's expertise with rain gauges, we'll get even better. And yet, people are still caught in harm's way. So we read about people getting caught by floods all the time. So perhaps there's some communication or social science aspect of this, and is that part of what USGS is going to be working on as well?
Yeah, obviously we do. And one of the examples was one I mentioned was Shake Alert, right? So given the ability to see something coming. Part of the answer to the question, though, has to deal with the human nature aspect, and let me give you a little sea story, as we would say in the Navy. And that I was in Louisiana as Katrina's approaching the coast, and I had my daughter there in New Orleans. Put her on a plane, and on that Sunday, the storm's coming. There's no doubt about where it's going. It's the next day it's going to hit. And so as I'm driving out of New Orleans, there had already been a mandatory evacuation finally issued, and so it said get out, right? Particularly if you're in areas that are sub-sea level. And so as I'm driving out past the Industrial Canal, I drive through a neighborhood, and people were partying in the street. And I remember looking at that thinking, this is crazy. And then the next thing I saw, which was the ultimate act of human hubris, was a guy waxing his car, right underneath the levee. And obviously that's not going to turn out well. And as I go out, I'm talking to the deputies that are there, and they said, we've been through there 3 times, and we've told them they have to get out, that it's not going to be good, get out. And human nature being what it is, sometimes they just make the decision to stay. And unfortunately, or fortunately, I guess in a way, it depends on how you want to look at it, we have the freedom to make those decisions for ourselves. But the thing that we can do is provide them with better quality and quantity, right? So in terms of the quality or qualitative assessment is this is coming, this is going to happen. The quantitative assessment is this is what it means. And of course we do that. And that's our entire hazards mission area. That's what we spend all our time doing, is really trying to characterize what are these threats, what are they going to look like in terms of their impacts, how do we mitigate, what are the things that we need to do now, how do we respond to them, what's the information that we need to do to get to the populace, because another element too is that if you say it too often, then people just ignore it, and then they say, well, it didn't happen the last time. which is what happens a lot of times in floods. Where I lived in Houston when I was working for NASA, we would get floods all the time, and the way the drainage system was set up and the intersections on the roadways, and people constantly drove into them, irregardless of the fact that they knew it was not a good idea. They just make that election. So we have to get better on getting an understanding of what the quantitative assessment is. This is what it really means to you, and the qualitative as well. As you mentioned, working with our partners in NOAA and elsewhere, so that we can get much better and more deterministic information.
I guess what we're talking about is something that NSF, for example, is calling Convergence Science, and you already mentioned trying to work on stovepipes and breaking them down. But if we're talking about vexing problems like how to get people to change their behavior and pay attention to a warning of hurricanes or floods or like that, it seems like that is a direction that many science communities are trying to move. And USGS, I see there was a movement for that in the area of geohealth is an excellent example of that. So what do you see as the future of, if you've adopted the term convergent science or call it anything else, in USGS?
Yeah, as you pointed out, one of the things that we've done is we've gone through the entire gamut in the history of the USGS, everything from specific disciplines as the more or less the mission areas to where we are now, which is the converged basic sciences in these mission areas that are the hazards and the land mapping initiatives and all those things that now have multiple elements with what you would consider to be the classic discrimination in the disciplines themselves. And so we're already doing that. And what we're doing right now is, as you're probably aware, we've got a reorganization that's going on in the Department of the Interior, which has taken a lot of patchwork elements of, we've just built it that way in all these different bureaus within the department that didn't align at all with each other. And so we've now gone to 12 regions which will align vertically within the department. And then horizontally is where all that coordination takes place, the convergence science, if you will. So Fish and Wildlife and Department of or Bureau of Land Management and the USGS all have the same interest levels across multiple parts of this, but now we'll be working within the same region, so now that's going to bring us together better. The other aspect of it is something that I saw today, and that is the science of decision making is becoming a larger and larger topic within the scientific community, and we're doing that in the USGS as well. I visited with our Science Decision Center this morning for about an hour and a half, and we talked through a number of these kinds of things, and very specifically things about how do you characterize threats like the volcanoes. And we walked through Kilauea because it took a trajectory we didn't anticipate with the flows at one point. And we were talking about Mauna Loa, the second volcano on the island. People forget that one, but it has some significant threat as well. So how do we get to, in the science of the decision-making process, it helps, one, the local emergency managers respond to it appropriately, get people out or give them the opportunity to get out quickly enough, but also more critically, how do we figure out, again, back to the question of why do people get caught in this, how are they making those decisions, and how do we help them get around maybe some of these mental roadblocks that are keeping them in place where they should be getting the heck out of Dodge, not waxing your car waiting for right. Katrina to show up.
So you mentioned briefly in your talk about the U.S. climate assessment, national climate assessment, and certainly many AGU members, probably many of the USGS scientists who raised their hands contributed to that. And I think many of us found it a little, maybe more than a little, discouraging when, White House Press Secretary Sarah Huckabee Sanders said that it wasn't based on facts, not data-driven, and that would like to see something that's more data-driven, that it was based on models. And you talked about working with climate modelers when you first came in. So what's your advice to your scientists, to the rest of us in AGU who are working on providing data streams to help constrain models about trying to communicate that basis for the science of climate change?
I'll start with really my personal position on that, because I got asked that when I went into the hearing in the Senate, for confirmation. And of course, there's a left and a right to these issues a lot of times, and it's all politics. And my position on the science is science has no politics. Now, we as individuals have politics, and a lot of times we allow that to enter into our position on the science, but in reality, like we were talking about with AR5 models and the presentations within the RPCs, which ones do you track? Well, that's the question, and the question really is driven by how well do we understand the science, and when we get into how well do we understand the science, what do we not know so that we can now go and investigate that so we get better results, right? Which gets back to the Convergence Science piece. And again, as we mentioned, in terms of trying to just go to Mars, we don't understand it well enough, and that's a true statement. But that doesn't mean we don't continue trying to get better and better at it. That's the mission of the USGS, is to get better understanding throughout. So from the standpoint, if I were to have somebody that was upset by the comment that might have come out of the White House for whatever reason, or a comment that came from the Congress, from House of Representatives, or somebody's on the other side of the political spectrum, which might be equally inflammatory if you wanted to look at it that way, even though I didn't necessarily think that Sarah's was all that inflammatory, but it could have been, and certainly other people have been. It doesn't affect where we are in the middle, which is the science. And the science has no politics. It's never settled. We're going to continue looking at it. We're going to continue marching down the path we need to get so that we can better characterize the environment, because we have to manage this environment as one of the resources that is the national domain that's outlined in the 1879 Organic Act. So stay focused on the science. That's what we're here to do.
Well, as a sort of a follow-up to that, I mean, certainly the models help us understand what we don't know, like you said, and that helps us guide, define future research. At some point, we also have to say, well, yeah, we don't know everything, but do we know enough to take some actions? Well, and when do we figure that out and work that into the scheme?
Well, there's the question, right? So how soon do you need to take actions? And that's where the argument gets into a lot of times. Interpretation of the when is really the problem. And the when really is a problem in what's that spectrum of time that we're dealing with. And time in this regard is probably the same as what was best described in how you measure depth in a seismic section, in that it's basically numbers on a rubber band, and you're doing one of these things trying to figure out where's the best fit. And our challenge is, where is the best fit, right? So depending on what's your time frame, and this is where the argument gets into, and this is where the science needs to focus, is what does it mean in terms of the big knobs, in terms of variables, and the 1,000 or so variables that were used in AR5, that number is going to go up just like they did in the previous AR modeling. In the reports, in terms of what's happening. And the next one, in AR6, we're going to have even more variables, but we're still not going to have them all, and we're still going to have a lot of uncertainty. So how do we address the uncertainty is really the question. And the question there gets to, do you want to take worst on worst? Do you want to take best on best? Do you want to take something in the middle? Well, it depends, right? It's really the bottom line. But in terms of being able to plan, we need to be able to go out as far as we can, look to see what that trajectory looks like, give us ourselves at least a glide slope that gives us a trajectory into the future, and then have something that gives us a feedback loop. And that's what we've been looking at, is how do we do that so that we now have a deterministic capability. So from the standpoint of getting to where we can manage these variables, that's really what we're trying to identify. One, I get the idea of what the variables are, what are the critical ones. When they start to diverge, obviously how we weight those variables is what the differences are. So how far can we push it where we can still keep it constrained to be something statistically significant, recognizing that any number of trajectories might exist past that point. Which one do we want to follow? Depends on your point of view and what you're trying to address, but recognizing that might be a condition you have to consider, you still have to loop back and say, what does our trajectory look like, and put ourselves on that glide slope somewhere. And that's the thorny challenge for us. But again, as long as we stay focused on the science, we hopefully will stay away from the political end member pieces, because that's our job, is to provide that science to the Secretary.
Sort of changing topics. This time, it seems like this time every year, as we think about the AGU meeting, we're also thinking about whether the government's going to shut down. And all those people that raise their hands then have to worry about whether or not they're actually going to be able to come to this meeting. Now, I know government shutdown is not something you have any control over, but what can we do to, or is there anything that USGS and other federal agencies can do to sort of manage the uncertainty so that the scientists can try to manage a little better whether their expectation of being able to attend a meeting like the AGU meeting.
Yeah, unfortunately, the problem with the shutdown is the statutory one in terms of how the money flows, and that unfortunately, if we're running up as we almost did on this one, where we would have been in a shutdown, that would have basically shut us off. And unfortunately, there isn't a lot we can do about that. We can't allocate money to be spent within a period where the government is shut down. It just literally doesn't exist as far as we're concerned. So the best thing we can do is one that's sort of good philosophy for everything is plan for the worst and hope for the best, and that's where we are with this one. Fortunately for us, we were able to pull this one off and push it down a little ways. Looks like we might actually see one potentially after Christmas. We'll see what happens with that. What I tell our scientists and what I tell people within the Reston office complex is we're just going to continue working right up to the point that they tell us that this is going to happen, because we can't shape the outcome on that. It's going to be really, it happens between the White House and Congress.
Just in closing, we're just about out of time, but I'd just like to give you a chance to talk to the early career members in the room. I know many of them probably aspire to follow careers in not only the geosciences, but maybe perhaps specifically at USGS. I assume that you're going to tell them it would be a great place to work.
It is a great place.
But maybe you'd like to say why and what sorts of things they could do to try to direct their career to reach that goal.
Yeah, as I mentioned, one of our initiatives is to look at workforce development. Everybody does that, but for us, it's a little bit more of a challenge because we have so many people that have been there for a long period of time. We need the new blood to come in, and the new people to come in. But as I mentioned, the great thing about the USGS for many of our young scientists is it's sort of a destination that they would like to naturally gravitate to. So from that standpoint, our biggest challenge is making the opportunities available and finding those pathways in. In fact, we have a program called Pathways where people come in as temporary employees to work on specific projects, and many of them are in the water environment or water mission area, but they cross the entire spectrum of all the things that we do. But what we do at the end of the pathways is you now have a pathway literally into a job in the USGS, and so that helps get them into the program. I would urge, if you're interested, to come to the USGS, take a look at the Pathways program, and because one will put you in a job that I'm almost certain that you'll like, and if you don't, it'll at least give you an experience there that will tell you perhaps maybe what you do like. And the one great thing about geosciences is the thing that I found out is that I loved it. And I look backwards, and all the things that I've been fortunate enough to do, I have never had a real job as a geologist at any point in my life ever, right? Now, I've always gone to work and enjoyed everything that I do. I go around and talk to people in the USGS, they all say the same thing. You know, there's always the day-to-day little irritations and stuff, but they've been there 40, 50 years, right? So obviously they've loved their jobs, and it is a great place to work. We score usually quite well on the satisfaction surveys. You know, every job could always be better, and that's one of the things that we look for is help us improvement. Come in and tell us how to do it. And we've got some big challenges, and one of them is the 21st century USGS, and that is to get us into that big data where we're ready to be able to push out the Internet of Action. That's a big, heavy lift for us, and we're going to need a lot of help. So we're going to need the young folks to come in and help us with that. So we really need you. Come see us.
Okay. Well, thank you very much for coming and spending this time with us.
Thank you very much. And
please join me in thanking Reilly.
Thank you very much.
Thank you so much. Yeah.